Before we dive into some of the more technical and mathematical inner workings of a correlation coefficient, let's just think about it conceptually and visually first. I created this graph from SPSS, but you can also create it in R, and it is from the dataset GRE and GPA, which is just an example dataset. It's really simple, located on SharePoint. We're going to use it to learn on and play around with. And it is a bunch of GRE scores and people's GPA when they get into graduate school. So we're trying to predict GPA from GRE. And this isn't the best example, quite honestly, only because it's fine for learning on, but it's not realistic because these are GRE scores from the old system. So way back when, prior to when most of you, I'm sure, took the GRE. It was on a different scale. And so you'll see some of the scores in there where the GRE is like in the 500s and 600s, which is not the case on the new scale. It's more like the 100s. So just to give you an idea, the mean of the GRE quant portion in this data set is 565 something, and the mean of the GPA is 3.3 something. And the correlation between these two variables is 0.61 approximately. So it's a nice healthy correlation. That's like 36% of the variability explained in one variable by the other one. So that's cool. And on the x-axis, we have the case numbers. So all 30 people in the data set, and then we have these lines corresponding to their scores and their GPA. Specifically, the GRE is the green line and their GPA is the blue line. And so then on the y-axis, we have the z-scores. So this is when both variables are standardized. And that just means they're linearly transformed and in such a way that their ranking is preserved. So when we standardize things, we make the mean 0 of each variable and the standard deviation is 1. And so that's what this depicts right here. And so when we see, like, for example, some scores that are 1 standard deviation or nearing 2 standard deviations above the mean, that means that these are relatively high scores. And then below the mean, it's the opposite. And so we can see some of these going into the 1 standard deviation below the mean. Now, I want us to notice, the reason I'm bringing all this up is I want us to notice the general pattern of data. And the general pattern indicates a positive correlation because, remember, when there's a positive association, as one variable increases, the other will increase to the same extent. So if one variable is 1 standard deviation above the mean, we would expect the other to also be 1 standard deviation above the mean, such that if GRE, someone scored 1 standard deviation above the mean very well, we would also expect GPA to be 1 standard deviation above the mean, or approximately. Now, to the extent that it is exactly perfect like that, it rises by the same amount, then we would have a perfect correlation of 1. And that is positive 1 in this case. And so this is a case of two variables walking together. And so we can see that, as one decreases, the other decreases with it for the most part. And then the opposite, as one variable increases for a given person, then we would expect the other variable to follow it. And to the extent that that pattern is broken, and we have, for example, in case 1, we can see that someone scored below the mean in GPA, but they got a really high GRE score, or pretty good score. I mean, it's 1 standard deviation above the mean. So they must have studied hard for the GRE, or they got lucky. I don't know. Maybe they just got into graduate school and didn't work as hard, even though they had the potential. So I'm just making up theories for case number 1 in this data set. And you can see that case 1 depicts the pattern being broken, where these variables aren't increasing together. One's going up and the other is going down. And Most cases, though, look like they follow the pattern. I think case 4, we have a little bit of a gap as well, where we have GPA really low and then not so low on the GRE. So there's this little gap here. So that's a break in the pattern, but not too bad. Now, if they were really far apart, then that would be a big gap in the pattern. Case 16 is a bigger gap where we have someone scoring a little bit below the mean on their GPA, but their GRE, they're above 1 standard deviation above the mean. And so, I don't know, about 1.3 standard deviations above. So this case represents where the pattern's being broken. And what this means is that if you deleted case 16 and case 1, you could rerun the data and have a higher correlation because you've eliminated some of the ones that are not following the pattern. Now you know how to manipulate data to make a higher correlation coefficient, R, which of course we don't want to do when we're publishing, but for learning, it's always okay to manipulate the data and try things out. So I encourage you to do this. Take out that CSV file, delete cases, rerun the correlation. Once you have the code, you're good to go. Just rerun it and just watch what happens in various cases when we delete things out that aren't following the pattern. But for the most part, that's why this correlation is so high. 0.6 is a nice healthy one. We can see that they're following each other, walking together pretty closely. And so okay, so here's something to consider as you're studying. If you were given a graph like this, could you pick out which data points, which places in the graph are problematic in terms of breaking the pattern? Because correlation is all about a pattern, and the ones that don't fall in line with that pattern are considered error or where we're not predicting as well. And so I'm going to show you in the next segment an example of a negative correlation where the variables are walking apart.